Hello, testing. Right. So I posted out the last assignment. So please start as soon as possible. And then hopefully by the end of this week, I'll release what you need to do in project 2. Okay. And then how we settle our project 1. I think we will do this announcement tomorrow because tomorrow will be more people. And soon I will release what definition and theorem sheets that I will give you in the final so that you can use that to prepare for your revision. Yeah, so that you know what you are given, what are not given. Okay. Okay. Actually, we have quite ample time for revision. Okay, so if you like, we can go for 2 revision class. Okay, which we can discuss the detail later. Our exam time is the last day of exam. Yeah, so we have quite a lot of time to prepare. 啊，上课考试哦，拜四不是最后一天。OK， is that Friday? Friday there's also. 嗯，OK， all right, right, cool. So I mean, so we have 2 more chapter to go. So the second last chapter is about infinite series. Actually, infinite series is what we covered in the first chapter in calculus 2. So it's good that if you can take those things to do some revision because we won't do much calculation here. We will just fill up the rigorous gap in calculus 2. So we will prove those tests that not proven before. Okay, and then we will introduce 2 new tests, which is the Abel's test and Dirichlet test. Okay, those 2 tests I will give some exercise to do in tutorial so that you know how to use them. But for example, like ratio test, P-series test, geometric series test, limit comparison test, simple comparison test, what else? Integral test, absolute convergence test, alternating series test. Actually, we proved some of them in calculus 2 already. So we will complete all the proof so that you know why they are true. And then you will see how epsilon delta get used, okay, in this topic. And then why we have introduced this topic, because later we're going to use this topic to check convergence for Taylor series. Okay, so it will be used later. So for this chapter here, we will go quite fast. I will just discuss the proof. Okay. So, so maybe let's recall one definition before we continue. So let's recall what definition. So when does infinite series converges? So we say that hello，怎么只有你一个人呢？喂，hello 啊，围着来哦，围着来的意思是今天来不来？哦，他来，他来。
我问到问题的关键。
我是数学老师嘛，对不对？Precise 终于是半路还是什么？那种可以要回来哦，他不是筹模啊？还是也是 OK，他有车了。哦，人家载他来。我大爷来了。哦，这样是搭车回来去 KL 还是？哦哦，还是 OK OK 好。 Okay, so we said that this infinite series converges if the n partial sum. So how do we write the n partial sum here? So sum, let's say n equals to 1 to m converges. Correct or not? Okay. So you see, when I say infinite series converges, doesn't make sense. Why? Convergence only defined for who? Remember? Only two things we define for convergence. What are the two things? Kuan we define convergence for what? Recall what we did in the first few weeks. Convergence of what? Sequence of what? 不记得 Yeah, sequence of what? AN AN 是什么？你记得只是你忘记吧？不是忘记啊，我讲什么废话？shit， 哦好，没有。Okay, AN. Last time we talked about AN. 什么是 AN? What is AN? Sequence of what? Real number. Okay, 所以我们 talk about sequence of real number. 但是 infinite series convergence 是什么意思 ？infinite series 是 number 嘛？它是 sequence 嘛？都不是所以 how do we define it? We define as a convergence of some real number. What's this real number here? What's the sentence here? What's the real number here? N partial sum. N partial sum 是个 real number 吗？为什么？ Sum of finite real number good 非常好，就有限个号码嘛，你可以加起来，对不对？加起来还是一个号码嘛，不会跑去无限的，所以它就是一堆的 sequence of number 咯。OK， 怎么造这个 sequence of number？就是你把前 n 先加在一起。That's all. Okay, so that now this will say that infinite series converges. So now we will go into a few cases. So I mean tests, not cases, tests. So how to test? I'll give you an infinite series. Tell me converge or not. How to tell me? Okay, so we have a bunch of lists here. Okay, we have a bunch of lists here. So you should recall from your calculus 2. Okay, so please take the calculus 2 content and do some revision if you forgot. Okay. Okay, so we will go through one by one. So first part, we will go through again one by one. First part, let's see. So first part is a test for convergence. Do you remember what test for convergence is? If the sum converges, infinite sum converges, then every term should diminish. Okay, the term inside your series should diminish. Limit of an should go to 0. So this is how we proved last time. Okay, even without epsilon delta, we prove it. We just use limit property here. So why this one says test for divergence, but the statement inside don't have divergence? Why this name is called test for divergence? While this statement doesn't have divergence inside here. Oh, use order. Okay. Use contrapositive. What does contrapositive do? If P, then Q become not Q implies not P. So what do you need to check here? So if you check that limit of Fan is not 0, then the infinite series diverge. Okay or not? Does it make sense? So actually we are using the contrapositive. But this statement is easy to prove. So we leave this statement on here. Okay, it's easy to prove. Okay, but you can use the contrapositive to apply. Okay, this is from calculus 2 slide. Exactly, I copy paste here. Then next thing we did last time is we showed that convergence series is actually this summation here is linear. Okay, what do I mean by linear? So if you have A and B, infinite series of A and B and converges, then if you multiply a constant, okay, to every term, okay, you ask whether this infinite series here converge or not. Does it converge or not? What do you think? Okay, it should converge. Okay, converge to what? Just C times the original infinite series. Okay, if I add, okay, or take subtraction of two term inside the infinite series that converge, still converge or not? Okay, converge. Okay, how to converge? Converge to the first infinite series plus or add the plus or minus the second infinite series. Okay, so this is what we have proven last time. Okay, so I suggest you, if you are not clear, please try and do your proof. Okay, please do proof. Okay, how to prove it? You need to go to the n partial sum. Okay, you can see that in the n partial sum, right? You can pull the constant out, or you can split the sum at each Sn. Okay, try and imagine what happened in x1, what happened in x2, s3, x4, s5, x6. Okay, you can pull the constant out every level. Okay, because every level is just finite. So finite, you can do linear thing. Okay, so we won't discuss this again because we have discussed it before, but we will discuss the next one. So the next one is so this one is for general convergence series. So the next part is we'll discuss series with positive term. Okay, so what does it mean by series with positive terms? What do you mean by series with positive terms? Okay, yes, without negative. So all the AN are positive. Okay, so we try to discuss the convergence of this kind of series. So let's say, when does this kind of series converges? We can give a necessary and sufficient condition here. Okay, what's the necessary and sufficient condition here? If there exists an M such that all the n partial sum is bounded above by this M. Okay, bounded above by this M. Does this remind you anything or not? Sequence that is bounded above by some M. Try and think back. What is a bounded sequence bounded by some M? What's that? Bounded sequence. And then convergence. Bounded convergence. What's theorem? What theorem? Monotone convergence theorem. Monotone convergence theorem says what? A bounded monotone sequence converges. Okay. So I give you bounded already. Do you have monotone condition here or not? Monotones means what? Monotone means what? Two conditions, right? Either the staircase go up or go down. So non-decreasing or non-increasing. So does this Sn non-increasing or non-decreasing or not? Ivan, does this Sn non-decreasing or non-increasing? Which one? Or not both? Non-decreasing or non-increasing? Non? Why? Why? Who is non-decreasing? Who is non-decreasing? Sn, right? Non-increasing means what?
Or going down.
Going down, correct. But you are, what is n partial sum? Keep adding. Wait first. But what thing you are adding here? Positive. So your Sn should be non-decreasing, right? Either you got 0 or you positive, 0 or positive. So actually Sn is a monotone increasing sequence. And it is bounded above, so it converges. Okay, no? Okay, so this is the other direction going up here using monotone convergence theorem. But this direction then, how to show? If infinite series converge already, can you find an M that bound every Sn or not? What M that works? What M that works? This one converges means what? This is a number. Okay. Can you find a number n that bound every Sn? Now what's the number you take? Sorry? Just take the infinite sum, correct or not? So the question here is it true that this inequality holds or not? Is it true? True or not? True, right? But this one converge, right? This is a number m. You take the infinite series, infinite sum, okay, to bound all your sequence. Does it make sense? Okay, no? Okay. Okay, so we have established this one if and only if. So the one direction, this one is obvious. The other direction you use monotone convergence theorem. Okay, monotone convergence theorem. Yeah. So did I write it down? I write it down. Okay, so for one direction, you can take M to be the infinite sum to bound all your partial sum. And then the other direction, we can see that Sn is a bounded sequence and also monotone because we are adding positive sequence, so Sn will keep increasing. Non-decreasing because sometimes maybe An is 0. So by monotone convergence theorem, Sn converges. Okay, converges. So Sn converges meaning the infinite series also converges. Okay, no? Any question so far? Any question for this proof? Okay, so in this case, yeah, so if you've got an infinite series with positive term, one way is you straight away check whether it converges. The other way is as long as you can bound all your n partial sum, then you are good. Okay, with one number if you can bound. Okay. So the next thing is a simple comparison test. Okay, so this test here, what is simple comparison test? Is if every term is positive, okay, for the two sequence is positive, and then an is bounded above by bn and bounded below by 0, then the series of bn converges implies an converges. Okay, you can think of it like the higher, how to think about this? The higher, you can think of it as a rectangle. Do you know how to think of this thing as a rectangle? You can think of this an, bn as a height of a rectangle. So height of rectangle of width how many? Maybe just width 1. Okay, width 1. So you can think of it like this. So should I draw on board? Oh. Things we got board today, I use for. So if you have this one, right? An greater than equals to 0, that's then equals to bn. Okay. So how do you think about this? So you can think of them as some rectangle. Rectangle of width what? So you can use rectangle of constant width 1, maybe. Okay, constant width 1. That. Okay. And then where is A1? Okay, you can maybe start your A1 here. So A1 here. Okay, maybe B1 here. Okay, and then A2. Right. A2. Maybe a bit higher, A2. But B2 for sure is higher. A3, right? And then maybe B3 and N3 is the same because can be equal, right? And then so on. Okay. So you can see that if the higher rectangle converge, the smaller rectangle should converge. Okay, so this is how you think about this simple comparison test. But how to prove it? Then you need to use the monotone convergence series to prove it. Okay, but the idea is like this. Okay, how you remember this A and B. Okay, so this one A4, B4. Okay. It is good to think about this way because later we'll see integral tests. Okay, we'll see integral tests. Okay. So first statement is Bn converges, An convergent. Then the contrapositive will be a infinite series of An diverges and then infinite series of Bn diverges. Okay. So this proof we also discussed before, so we won't pursue it again. Another proof we have seen is this limit comparison test. So what's limit comparison test? How is it different for simple comparison tests here? So you can see that this statement here is limit comparison test. So meaning you need to compare with limit. Compare with limit. Okay or not? Compare with limit. So how to get this limit here? So what can you do is you take An over Bn. Okay, so you look at the ratio between each term. Okay. So the surprising result is if you can find this L and then this L is a finite number between 0 and infinity, then these two series converge or diverge together. Okay, together. But if this L is 0 and also Bn converges, only then An converges. Okay. So L equals 0 got extra condition. You need the denominator to converge first. Only the numerator will converge. Yes, question?
If I change the condition,
What condition?
An and Bn, they are close to, no, I mean, less than 0. Is that the result is the same?
Less than 0, huh? Okay, think about it. Think about it. Is it possible that this limit less than 0 or not? You need to see what An and Bn we are using. Both An and Bn is positive. Okay, so infimum of positive number is what? Only you can get 0. You cannot get negative because negative and 0 still got some distance, but you don't have negative number to achieve that. Okay, so you won't get the case less than 0. But it's a good question. Okay. Yeah. It's a good question, but you won't get the case L less than 0. But you could get a case L is infinity, but by the way, could diverge. If diverge, then nothing to say. All this statement say nothing about those cases. Okay or not? Okay, we only talk about when this L is finite. Okay, it's finite, and then when it is 0, that's all. Okay, this is the content of a limit comparison test. So, I mean, you can think about this second statement here. Why, when L equals 0, I still need Bn to converge so that I can say An converge? What does this mean? When L equals 0 means what? Bn already 已经大过 An for 每一个 n 还不够哦，这个 statement 说还不够。如果你要你的 numerator converge 还不够，你还要它整体 denominator 的 sum 也 converge 才够，明白吗？ Does it make sense？ 这一个 L 等于0的时候已经可以让你的 Bn 比你的 An 大了，但是大是每一个 term 在 compare。Okay？ 然后这个 statement 说不够，如果你要 check An converge 不够，你还要多一个 condition， 你连你的 denominator 的 partial sum 也要 converge， 它们加起来的号码也要 converge。OK， 这样你才可以确保你的 numerator 的 series converge。Okay or not? Does it make sense? Okay, so you need extra condition, okay, when L equals 0 for An to converge. But if they grow with the same ratio, then they will converge or diverge together. Okay, together. Together. So, I mean, you can ask the question, right? Can I swap AN and BN or not? No? Yeah, so this is the point here. So that's why we put AN at the top here, because we allow some of the AN to be 0. Okay, yeah. And then we won't allow BN to take any 0 point here. Okay, so this is the point here. Okay, good. Good, good. Okay. Right. Right. Okay, I think this is the first proof for the day. Maybe we'll prove this and then we will take a break. So the first proof of the day is this integral test. Yeah, and then we will show you how we use the boot integrability. Okay, let's move this guy. Let's prove this first proof of the day. Okay, so let's prove this integral test. So what's the content of an integral test says? So f have to be continuous, positive, decreasing, okay, function on the interval from 0 to infinity. And then what's the sequence we consider? We consider the sequence at f1, f2, f3, f4, f5, f6, x7. So f on this integer value, okay? We call it an. And then we try to sum them up. And then we can compare between infinite series and improper integral. So you remember how we define improper integral or not? Huh? How to define improper integral? What's the definition of it? We define improper integral as a limit. Okay? Limit of what? So on one side is 1, right? The other side is infinity. But the integral we learn is what? On the closed interval AB. Okay? So we need to close one side first. Okay? We only close, we need to close on two sides. We already close on one. The other side, we close with some B. Okay? But we want to compute up to infinity. So I take this integral to limit from B to infinity. Okay? Does it make sense? Okay. So obviously, when f is continuous at on 0, 1 to infinity, implies that it is also continuous on 1 to b for all the b in between 1 and infinity. Okay, does it make sense? So continuous means what? The function is integrable. Okay, so it's integrable. So such that this is defined. Okay, so the boot sum is the boot integral is defined because it is integrable there. Okay, and then for every b I got a number, right? I consider the limit. Okay, I consider where this number go. Okay, so the content is the infinite series an converges if and only if the improper integral converges. So what's the picture here? So what's the picture for this integral test here? When I speak about this adjective, so you should think about what's this function could look like. So what's this function could look like from 1 to infinity? Can everyone see up to here? Can see up to here now? This line. And okay. So how does this function looks like? Continuous, positive, decreasing. Can anyone do some gesture about this function here? Oh, okay. Positive above the x-axis and then decreasing. Okay, continuous. Okay, normal. Maybe normal. Okay. And then what? What's this series here? Series, how to define? AN equals to Fn. N is what? Positive integer. So you need to get your positive integer in your pocket now. Okay. And then where is F1, F2, F4, F5, F6? So these are exactly the point here that the F would take. Okay, so here we got A1, so F1, which is A1, F2, which is A2, and then A3, A4, A5, A6, and so on. Okay, so you continue, right? Okay, now, does it make sense? So you see, sum of AN is what? AN is the height. What is the width? You can think about it if you want to think of it as a rectangle. AN times 1. Okay, so this is what actually, this is like a upper sum. I don't know. This is the upper sum. If you consider your partition using this positive integer, this is like the upper sum because your function is decreasing. Okay, your function is decreasing. Okay, so this AN is upper sum actually. Okay, so the content here is what? The content here is if this upper sum converges, then the area under the graph also converge. If the area under the graph converges, the upper sum also converges. Make sense? Okay, the upper sum also converges. Okay. Okay. Okay, let's think about how we prove it. Okay, let's think about how we prove it. So which direction we want to go? Okay. So let me see. How should we start? Okay, so we have spoken so much. So let's write down the real work here. Okay, let's write down the construction and then we will prove this theorem. So let's do the same construction I have on the board. So so we will denote to this n, we will denote xn as the partial sum. Okay. AK, in this case, I call it AK. Okay, to be the sum of k equals to 1 to n of fk. Okay, so this is the n partial sum of infinite series of an partial sum for infinite series a k. Okay, and like what I said just now, how to realize this sum as upper sum. Okay, how to realize it? So exactly, we introduce this Pn. Okay, the partition. Okay, of 1, 2, 3, dot, 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 up to n. Okay, be the partition, the standard partition. Okay, the standard partition of 1 to n. Okay, so note that we said that f is decreasing and positive, right? So it's decreasing and positive. So how do we compute the upper sum and lower sum here? Okay, how do we see the upper sum and lower sum here? So you can use this picture to guide you. Please use this picture here. So what's the lower sum here? Okay, if you use this partition, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. Where's the lowest point? Where's the lowest point? Well, I haven't asked today. Right? Seng, where's the lowest point for lower sum? In the interval of xi minus 1 and xi. Xi minus 1 to xi. Where's the lowest point? This function is decreasing. Xi, right? Okay. So in this case here, what do I write? So here we use what's the notation we use here? Let me be careful a bit. So we will use let me be careful. So okay, so we'll use fi plus 1 here. Okay, times 1. Yeah, is it fi plus 1 or not? So I is starting from 1, okay, and then 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so between I and I plus 1, so we will take between I and I plus 1, we will take I plus 1. Okay, so in this case here, we'll get f2, f3 plus dot 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 up to fn. Okay, is it true or not in this case? If you look at the interval from 1 to 2, where is the lower sum? The lower sum you take is this a2 here. Right or not? This a2 here, the lower sum. Okay, so lower sum, I use green line here. Okay, lower sum here, lower sum, lower sum, lower sum. Okay, so you take f2. Does it make sense? Okay, no. Lower sum for the first interval. Okay, so it's like you shift to the next point. Okay, but upper sum is what we discussed just now. So upper sum is exactly fi times 1. Okay, so you start from f1 plus f2 plus dot 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 up to fn minus 1 here. Hey, these are the finite sum, correct? No? So how does this compare to Sn? So in first case here, this is really just Sn minus the first term, correct? No? The second one, as what? As f1 up to fn minus 1. So you add from the first term up to what do you mean by second? So n minus 1, exactly n minus 1. Okay or not? Does it make sense? Okay. So you can see how we study this integral test using our the boot upper sum and lower sum. So since f is continuous, right? Continuous on this interval 1 to n, how do you compare between this integral of f dt with this uf, with this upper sum and lower sum? Where should you place the upper sum and lower sum? What is the relationship between upper sum, lower sum, and this the boot integral here? Sydney, any idea? How do you compare upper sum, lower sum, and this the boot integral here? Upper sum should be greater than this integral or lower than this integral? Greater, right? Okay, good. So it has to be greater than this integral. And how about lower sum? Should be lower, good. That's why we call it a lower and upper integral. So in this case here, what do we get? We actually get a relationship between this partial sum with our integral. In particular, Sn minus 1 is greater or equal to this double integral, and then greater or equal to Sn minus f1. Okay, so this is the inequality we get between between what? Between the infinite series and integral here. Okay, so we bound our integral using two partial sum with some adjustment on the other side, such that we throw away the first term. But that's fine, right? If it converges, I throw away first term, it still converge. Okay, throw away finitely many first term is still fine if it converges or diverges. Okay, so we got this result now. So let's do one direction. Which direction? So let's prove that, want to show that, this direction is what? Want to show that if the infinite sum converges, implies that the infinite series converges. Okay. Right. How to do this? So we need to make use of this bound here. We need to make use of this bound here. Hmm? So I mean, one direction you could pursue is like Sn minus 1 should be less than this infinite sum, right? Correct or not? Okay. So meaning what? This integral is bounded by a number, bounded above by a positive number. Okay. Bounded below by what? This function is positive. We have proved that if a function is positive, then the integral is also positive. Okay. So you are positive, you are bounded by some number. If this number is 0, then I'm good, because like squeeze theorem, it is 0. But if this m is not 0, some positive number, how? We cannot deduce, actually. Okay, we cannot quite deduce it. So instead, we will use a contradiction. Okay, we'll use contradiction here. So suppose, on the contrary, this integral diverges. So what do we mean by a sequence diverge? What do you mean by sequence diverge? For every m, this integral is greater than the m. Okay, so let m greater than 0, then there exists a point Sm such that the integral from 1 to xm ft dt is greater than m. Okay. 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 Yeah, because this integral cannot have a divergence such that like 1 negative 1, 1 negative 1, 1 negative 1, because our integral is adding up positive area. Okay, so it is increasing. Does it make sense? So when it diverges, it must diverge to infinity. So I'm using divergence to infinity. So 你要怎么说你去到无限？你怎么去到无限？大过每一个正整数或者正数，OK，大过每一个 positive number，then 你才是无限。 不然的话你小过一个 positive number 你还是无限嘛，你就不是了。OK，你要必须大过每一个。OK，right. Then where's the contradiction here? How to get contradiction here? How to get contradiction here? How to get contradiction here? You see, look for this inequality here. You see that this the middle guy already diverge. Then you should see that the last guy also need to diverge. If this last guy diverge, what happened? Sn diverge. Okay, but we assume that Sn converge. Okay, so you can see that if we choose n greater this than this point Sm here, then what do we see is we have xn greater or equals to integral of 1 to n plus 1 ft dt. This is just using the relationship here, n and n minus 1. Okay. And then this integral here should be greater or equal to the point from 1 to xm plus 1. Okay, because we pick n is a term, is a point behind xm. Okay. And obviously, this guy here is greater than the integral from 1 to xm ft. Okay, so this number is greater than m by assumption. Okay, since m is arbitrary, so since m is arbitrary, okay, this is true for all m, then our infinite series should also diverges because our partial sum already diverge. Okay, does it make sense? Okay or no? Okay, so the divergence of an integral will result in the divergence of n partial sum. Okay, any questions so far for this one? Question or not? Any part you miss out? Oh, okay. So we'll continue to the other direction. So the other direction will be proving that which direction is this? Yes. So the direction is you want to show that if the integral converges, then the partials, the infinite series also converge. Okay, also converge. Okay, so if you go back to this series here, what can you see? What can you see here? If this integral sum converges, meaning what? This series is bounded above by a number. Okay, and then this number also bound Sn minus f1 here. So meaning what? Sn is bounded by a finite number plus f1 is still a finite number. So just now what we have proven, if my n partial sum can be bounded by a number, that means my series converges because bounded convergence, bounded monotone theorem here. Correct or not? Does it make sense? Because what is Sn here? Sn here are all positive term here. All positive term. Okay, as long as you can show that this Sn is positive, is a series of positive term, and then it partial sum increases, okay, and then bounded above by the integral, okay, is bounded, so it's a bounded monotone sequence, so the n partial sum must converge. Okay or not? So let me write down here. So converges, so not that xn minus f1 is less than or equals to the integral from 1 to n ft dt. And then this guy here should be less than 1 to infinity of ft dt, which is a constant, okay, because it converges. So Sn is bounded above by a number m plus f1 here. Okay. So by bounded, so by monotone convergence theorem, since Sn is increasing, okay, increasing. So Sn converges. Okay, meaning, so that means, so by definition, hence by definition, the infinite series also converges. Okay. All my order swap. So since Sn increasing, then by monotone convergence theorem, Sn converges. Okay. Hence, by the definition of convergence of series, the infinite series of An converges. Okay or not? Okay. Any question before we take a break here? Any question? Any question? Okay, if not, we will take a break here. So let's break until 1:16.
很忙到郁闷。
唉，太忙了，上个礼拜。
就这样，
准备考卷哦，然后要改
我可以
assignment。
帮你准备。
你帮我准备考好它就可以了。帮我准备考好它就是最好的。没有啦，还有 assignment 哦，还没有改，要改完的。准备开始改你们的。这个礼拜还要再忙一个礼拜。assignment 应该做到七七八八，但是就剩 tutorial 还要做。我觉得他没有收回来怎么改。
送回来交。
对 project 其实交要定一个时间一下。因为我还没有给你们 turn it in 去 check 你们的 project。
我要最低定。
当然要啊。
我要是你没有放我就没有考过去。
啊？
我以为你没有放我就没有了。
不可能。
因为你一开始你就给你跟他放 error key 什么东西，你会放这种。
Error key
就是turn in 的 error key。
哦，对。我要去看一下我的。
还有一个 project two 啊。
对，还有一个 project two。
这不是删了。我觉得就是你给 project two 只要给。
已经给了，就是做一个最后一课的 summary，我会给你们范围啊，你们就读那些 chapter，然后做一个总结出来就好。
那编辑线都是自己选的。
自己选什么意思？
就他讲你要有包括什么地方。
我会给你们一个大纲，你们去跟哦，然后你们可以写多了，但是不可以写少啊。对，就这样，就是该读的东西要读到，如果你觉得这个很有趣很好玩，OK 放进来可以。但是总的来说 ，Project Two 的 idea 就是让你们去做最后一课的温习，就拿来做温习，然后总结啊，系统性的做 note。没有像写 paper 这样啊，没有这样哦，就是普通的一个 summary，能放一些 definition example 啊。
每个人 definition 这样子，每个人做的东西都差不多一样。
差不多一样，差不多一样。
对，意思就是可以抄。
当然就不是这个意思咯。当然就不是这个意思。
你要理解没有？你问老师你是可以的，你问老师你就不可以。
没有问也不可以，没有问也不可以，没有问也不可以。 那就不可以抄这个东西不可以跑进来。
可是我不得空，我的 not 一发10分钟，老师你不要我的 not。
什么意思？
昨天那那个 not
啊？not？
这是我的 not，engine not。
对，然后
现在是全部都是那种，全部都是这种东西，
什么东西？
就那种世界的铁律放在那边，是我好奇耶，
你好奇
就是这样我这样 run 啊，其实是
对
有人是人为掌控的秩序，还是原本这个世界的秩序就是这样子的？
你要这样讲的话，应该可能是说，大部分人想跟的秩序。喂，Hello，赶回来了。
现在在讨论有没有来，你来了，但是有没有？
就是
不上这么一点。
那个什么课？
花经济学。
哦，
没事，我还没有看过。我也
那个铁律啊，那个铁律，怎么讲哦？可能是大部分想要讲讲，你也是做过 leader 嘛，你应该知道嘛，对不对？
对，
呀，就是有一
因为我
些东西
知道，所以
啊，
看这种戏的时候，我就已经就是大概都会发生的事情，然后中心思想这种，就大家大概就在听我，
是啊，
差不多。
你说这个铁律怎么来的？就是这种社会
好
的，
像每个人都在跟着做
对
这个法律，还有说这个秩序，
对，
但是这种行为，然后跟着去做，
然后
就是这种我觉得这成为世界的铁律哦，就是它不会变的，就全部人都是跟着它。反正是有种感觉，是前面有一种成功的例子啊，全部人就 follow。
哦，
可是你又不懂那个，其实要其实有限制性，
比如说，
比如说，for example，马云啊，
对
他没有读完书就辍学去国外读书，就是他没有出去，他做这样强，可是至少他有人脉，他有钱，父母送他去国外读书。在国外读书的时候，他是成绩很好很好的那种，可是很多人都看到哦，比如说哦，他没有读完书，他就辍学了，然后他就做这样子，好像别人把他当做一种铁律来看，然后就会很多人 follow up 这种东西。
你是说他没有看到他背后的其他的？
对
，OK，
就说假设后面的资本的感受还是什么，
确实
我特别好奇，这种铁律是人为的还是自带的？
你讲人为是说，
就是
因为被舆论言论带偏向这样的。
会有，就比如说那种他们有权有钱的人，他们掌控整个舆论
啊，
会导致现在生活变得越来越想变成大家所想的东西，这种就是人为的掌控。
OK，我可以讲是有，蛮大部分是这个原因，蛮大部分是这个原因。所以呢，所以你想怎样呢？蛮大部分是这个原因。
就我讲的东西啊，我们身在其中，但
对，
随波逐流，但身不由己。换人讲就是
对，
这样的感觉就是哦，你只能 follow up，但是你又不想 follow up。
对。然后呢？
来了，
古代哈，但是至少给我的阶段来说，我讲讲哈，感觉还是想做出一些什么改变啊之类的。
每个人都想做改变嘛，因为全部人都
没有每个人，
大部分人
没有，也没有大部分人，只有小部分人吧，
就是
想要做这个改变。
因为讲的for example，全部人比如说今天这个东西可以赚钱，然后就还要个义务感的，为什么？因为他们不甘于做，想要做大钱，比如说做富翁这，真正能做到这种东西的没有。
对，
可是就是全部人就会为了心中那种你不甘心，你不满意，的事情。所以我好奇，这个是人的本性就会是这样子，还是因为他们那时候是资本家掌控，让我们变成这样？
不，这绝对是人的本性，我已经相信这东西，因为你要让一个人改变这不是这样简单的。你要让一个人改变，是那个人要改先，所以那个肯定是人的本性，他已经 有这个不甘，已经有这个想要去做的事情，然后你再煽一下风，你才会点燃，才会让这个变成一个成熟大火。不然的话，你很难点燃一个东西。如果一个
舆论是女生的购买力大于男生，
然后
这个好像是之前资本家有做过这种调研，然后会导致现在的资本家就不说，有些女生会想说，哦，你不买这种，你不说节日你没有送礼物给我，那你就是不喜欢我这种。这种好像是资本家导致舆论，导致他们现在100年以来他们就会有这种观念，可是在之前的观念是没有的。这种算是理性的一种还是什么？我感觉好像是。
比如我给你一个 example 啦，就是说，什么叫做男人一定要在外面打拼，女人在家顾家，这个也是一种舆论出来的东西啊。
那个他们日本做给女生买包那种东西，
就是
他们
有些确实是感觉是人家想要制造一个他们要的 society，所以他就给了这种 notion 出来。但是如果你真正去 observe 的话，也有女生在外面做工，男生在家里。
对啊，就以现在来讲会，因为
对不对？
现在女人的关系会有这种，
所以呀，很值得去探讨的，很值得去探讨。呀，
人的本性会与这种不一样。
但是我想讲的是，人的本性不会因为这种舆论而讲呢，永久的带偏啊，他偶尔又会转回来。
也就是被比较那个东西
很难讲。啊，确实应该是对的，那是确实。
然后我发去的时候，有朋友说，有没有考虑去打一个哲学家？
就讲，我现在在读这数学。Okay, so next thing we will discuss is so you quickly run through this P series here. Okay, what's P series here? If the series have the form 1 over n to the p, then it is a P series. It converges if p greater than 1 and diverges if p less than equal to 1. Okay, so what's this n? What kind of n we can take here? Any natural number. Okay, yeah, this n only live in natural number, correct. Okay, so this n is natural number. Okay, n is natural number. So this proof we already proved it in calculus 1, so we won't discuss this proof also. Okay, so yeah, we won't discuss this proof. So this n is in natural number, by the way. So let's make it clear here. So n is equal to 1 to infinity. Okay, good. Right. So we have finished discuss a series with positive terms. Next up, we'll discuss series with arbitrary term. Also can have negative term, zero term, positive term, all possible cases. Okay. So we'll talk about series with arbitrary term. Huh? Yeah. So remember last time, how do we discuss this kind of term? We got discuss some things like alternating series tests. So alternating series test mean I got positive, negative, positive, negative, positive, negative, positive, negative. But here, arbitrary terms can be positive, negative, 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 positive, negative, positive, positive, positive. So any combination, I mean, okay. So how do we discuss this kind of test? So one notion we introduce is converges absolutely. Okay, converges absolutely. So what is convergence absolutely means? So let's take a series. Maybe I don't know how to compute this series here, but let's say if I just consider the absolute value of an. So this means what? I go back to the case of series with positive term. Okay, so we can check using all the tests we have introduced just now. Simple comparison test, what test? limit comparison tests, integral tests. If you use those tests and then check that, oh, sum of absolute terms converges, then we will say that the original series converges absolutely. Okay. Converges absolutely. Okay. So maybe you ask one question or you ask one question. Hey, this guy, the absolute value of this guy converges absolutely. But my question is, the original series converge or not? You haven't answered me. Correct or not? So any relation between convergence absolutely with the convergence in the first line or not? Any relation or not? What do you think? Can I tell something about the convergence of the original series or not? What do you think? Otherwise, this thing is almost useless. So it cannot tell me about the original series. I still remember. Sure, it's in between. Then still don't know whether the series converge or diverge. Can I get a definite statement or not? Or if it absolute converge, then what? Can you tell me about convergence of the original series or not? What's the test we learned? What's the test we learned last time? What's the absolute convergence test says? What does the absolute convergence test say? Calculus 2. And an absolute convergent series converges. Okay. So meaning what? Meaning what? Meaning if the sum of absolute term converges, that means your original sum also converge. Good or not? Like this, good or not? Okay, so absolute convergence is stronger. That's why we name it as absolute convergence. Absolute means what? 最大的 ，OK， 就是 absolute， 怎样讲完全它已经完全 converge 了，将它原本的那个应该也要 converge。OK，absolute convergence。Okay, we will prove this later. Okay, we will prove this. I mean, should we prove it now? So let's introduce one definition before we prove it. So what if where's my definition? What if, let's say, if a series of an converges, but the sum of absolute value of an doesn't converge, what do we call it? Still remember? It converges conditionally. So a series that converges but does not converge absolutely, we say that it is converge conditionally. Okay. So how do you think about this logical equivalence here? So we have what? We have convergence converges absolutely implies convergence. Okay. But if you have P, then you have Q. But you can have Q but don't have P, correct or not? False can imply everything, correct? So in that case, we will say that the series is convergent absolutely. Okay, converges absolutely. Okay, if not, so here is P implies Q. So if not P and Q, then this is what we call converge conditionally. Okay, if you have P, you must have Q. Okay, but you can have not P, but Q happens also, then it converge conditionally. Okay. Okay, right. So we will prove this absolute convergence theorem now. So before we prove that, okay, before we prove that, we will prove another theorem first, which we will use it. So the test is, so we'll prove this test. So it is the Cauchy test for series. Okay. So this Cauchy test for series, you should remember what's the Cauchy criteria for sequence. What is Cauchy criteria for sequence? A sequence is convergent if and only if it is Cauchy. So what is Cauchy? Cauchy means what? For every epsilon greater than 0, there exists an n such that for any two terms behind the n, for mn greater than n, the absolute value of am minus an is less than epsilon. Any two terms after n is less than, the difference is less than epsilon. So it is also similar here. So it is also similar here. So we just replace the sequence here with what? N partial sum. Okay, we just replace it with n partial sums here. So a series converges if and only if there exists an epsilon such that for every n in n, such that for all n greater than n, then we can, without loss of generality, we assume m greater than n. Then what? Then the sum from k equals to m plus 1 to m ak is less than epsilon. Okay? So I claim that this proof is immediate. Why is it immediate? What's this term here? This is just Sm minus Sn. Correct or not? Sm minus Sn. Correct or not? Okay. So it follows from, since the inequality is true, okay, since this equality is true, the result follows from convergence, Cauchy convergence of sequence of real number. Yeah. Any question? Any question? Please, I need question because the way I'm teaching is different from the other lecturer. The other lecturer maybe asks you to regurgitate only. You know what is regurgitate? Regurgitate, do you know what is regurgitate? 牛嘛，牛怎样吃东西，你知道吗？它吃了还要吐出来啊，再咬了再吞进去，你明白吗 ？regurgitate，OK，我要你做的事情是 internalize， 听过这句话吗 ？internalize， 什么叫 internalize？ No， 不是拉出来，你要吸收它的营养，明白？你要明白，你要理解，你要吸收那个营养，你拉出来就没有用啊，吃拉。OK， 但是我不要讲你啊，但是有些人瘦就是这个原因，因为他一吃下去他就拉，他没有吸收到什么营养。我没有在讲，他说我在讲很多个你。对，真的，这个是事实来的，这是事实。你们为什么瘦，是因为你们真的是没有拿到那个营养。对，你去问医生，医生也是这样跟你讲啊。 对吧？啊，我不是在贬低你，我是在讲一个 fact。你去问医生，就是这个意思。哎，但是不要担心，你总有一天会变肥，因为我看到我朋友已经变肥了。瘦的朋友没有啦，不是讲变肥啦，就比较发一点的，发福一点，因为人的新陈代谢变慢了啊。哦，呀，虽然你不能够吸收到营养，但是问题是你也排不出去了，所以它就留在那边了。OK，所以这个就是一样，所以你必须要 internalize 啊，我讲的东西，所以你必须要问我，OK，一定要 make sense to you，OK，make sense，OK，internalize，right，so OK 吗？Everyone follow this argument here. I will write down full argument inside my lecture note, but the idea is you should use the Cauchy convergence of sequence in real number. Why? Because if you regard Sn as a sequence of real number, you want to talk about sequence of real number converges, then for OMN greater than n, Sm minus Sn should be less than epsilon. But what is Sn minus Sn here? It's just the last few sum from n plus 1 to n. Okay, so this is the point here. Does that make sense? Okay, I just use a different way to express Sn minus Sn. Okay. Yeah. But this is good. Why is this good? Okay. We want to use it to show this test here. Okay, this is good. What we have just now is good. Why? So if you can consider this guy here. So for O n in n, and then sum from j equals to n plus 1 to n plus k. How do you look at this sum here? This bit of sum here. Okay, this chunk of sum. This chunk of sum, you can view it as a less than or equal to the sum of absolute value of aj. Why? What did I use here? Why my absolute value go inside? What did I use here? What did I use here? Triangle inequality, correct or not? Okay, sum of AB is less than or equal to the sum of A plus sum of B. I mean, absolute value of sum of AB is less than or equal to the absolute value of A plus absolute value of B. Okay. Okay, but why is this good? Why is this good? Why is this good? By assumption, what do we have? Since the infinite series of absolute value of AK converges. So by the test just now, what happened? By the Cauchy test just now, we know that series, we know that the sequence of partial sums, sum of this series is a Cauchy sequence. Where is a Cauchy sequence? Where is a Cauchy sequence? Where is a Cauchy sequence? So you see, the right hand side is a Cauchy sequence. How left hand side? You can also bound the absolute value using the right hand side guy. Okay, if you can make the right hand side guy less than epsilon, you also can make the left hand side guy less than epsilon also. So this means what? This means by the inequality above, the sequence of partial sums. So for example, we will write the sum of, let's see, what do we write here? Sum to j equal 1 to n plus k. The sequence of partial sum, okay, for the series k from 1 to infinity of ak is also Cauchy. Okay, it's also Cauchy. Correct or not? Okay, it's also Cauchy. Okay, it's also Cauchy. Because if you can make the right-hand side less than epsilon, you also can make the left-hand side less than epsilon. Okay, for any terms from n plus 1 n until n plus k. Does it make sense? And then this is true for all nk. True for all nk. Okay, so yeah. Okay, so again by the Cauchy test for series, it follows that the series AK converges. So the technical part is to show that this partial sum of AK is also Cauchy. Okay, so this is a technical part. If you want to write down the epsilon argument here. Maybe I will add it into my lecture notes. Okay, so you can see the full argument. You can see why is it Cauchy. But can you roughly see from this this inequality why is it Cauchy here? If I can make the right-hand side smaller than epsilon, surely I can make the left-hand side less than epsilon. Does it make sense? Okay, yeah. Okay, so you can, I mean, what you need to get is this kind of result. You need to get this result for infinite series of an, okay, using, you know that the series of absolute an is less than, is Cauchy. Okay. Any question or not? Any question? Any question? Yes. Yes. Yes, that's right. That's right. That's right. Yeah, because the sequence of real number we consider here are n partial sum. That's right. If you don't like this nk, right, really you can just pick m greater than n. Okay, you can make m and n easier. Okay, I will write down a proper one later. But if you want to use nk, is also fine because you know why I fixed an nk here. Because I just want to demonstrate how far m is from n. If I write like this, but it's okay if I don't know how far m from n is. That's fine. Because we just need to make sure for all mn it works. So if it is mn works, nk also works, then they are equivalent. Okay. Yeah. So so what I want to say is n plus 1 to n plus k is a different way to express m and n. Okay. Okay. I mean, if you are a bit worried, in this case we use mn, why in this case we use nk here? It's just that I express m as n plus k. Okay, if you want to relate the two. Otherwise, I will change my proof to mn. Okay, so that you can follow easier. Any question so far? Now we were going quite fast because we need to use what we have learned before. Okay, we need to put all what we have learned before together now, make into a better use. Okay, what time is it? 1:39. So next proof is about the ratio test. We didn't really touch how to prove ratio test last time. So what's ratio test? Let's remind ourselves. So you see, ratio test here is concerned about series of non-zero terms. Okay, non-zero terms. So non-zero terms means that It could be positive, could be negative, but cannot be zero, that's all. Okay, so if there's no zero there, then you can do some division. So what kind of division we are doing here? We are looking at the limit of consecutive term. Where limit of consecutive term. So how do you compare A1 to A2? A2 to A3, A3 to A4, A4 to A5. Okay, if the limit of this absolute value of this ratio here is equals to something less than 1, okay, something less than 1, that means what? The series converges absolutely. Hey, can you imagine when this limit less than 1? Can you imagine when? When the one below is larger. Okay, the one below is larger. The one above is smaller. So that means when you compare consecutive term, the term getting smaller, smaller, and smaller. How small it has to go when this limit equals to some L less than 1. Okay, then the series converges absolutely. So meaning what? Meaning the absolute value of this AN also converge. So if this series converge absolutely, this series also converge by absolute convergence test. Correct or not? Okay, so we know that the original series also converge. Second, if this L is greater than 0 or worse, go to infinity. Okay, then the series confirm diverge already. Okay, because every term is like growing, 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 and growing. Okay, it diverges. How about the last one? Equals to 1. What happened? The ratio, the limit of the ratio is equal to 1. It grew somehow similarly every time. Then we don't know. We cannot say anything. Okay, we cannot decide. Sometimes converge, sometimes diverge. Okay, we cannot say anything. Okay. So the point here is you need to look for less than 1 or greater than 1. Okay, for this limit. Equals to 1, then you need to change your test. Okay, so we need to prove this. So before proving this, we need a lemma here. So we need a lemma. So let's put a lemma here. So take a series. K equals to 1 to infinity. AK. Okay. And then suppose that there is an R such that this R is in between 0 and 1. And there is an N in N such that for all n greater than or equal to n, an plus 1 less than or equals to r of an. Okay, then we will say that the series AK is absolutely convergent. Okay, absolutely convergent. Okay. What can you see here is this one is quite close to our ratio test statement already, right? Quite close already. Okay, but in the ratio test statement, you have a limit like this. So in ratio test, the statement we have is limit this. So the difference is here. Okay, so later we need to do some adjustment to deal with this limit here. Okay, so this lemma is very rigid. Okay, rigid, there's no limit here. So it just says that an plus 1 is less than or equals to r times an. Okay, very rigid. But in the ratio test, we need to have this lemma, have this limit property here. Okay, so later we'll see how we apply this. But I think today we'll just prove this lemma first, and then we will resume tomorrow, I guess. Okay, so let's try. So let's see how we prove it. So how do we prove it? Okay, so I mean, first, what can we see here? So we can apply the inequality multiple times, okay, so that we can get the absolute value of n plus k, okay, and then it's less than equals to the rk times the absolute value of an. Okay, can everyone follow this? Okay, so you can apply this multiple time, right? For example, you can look at what happens to a of n plus 2. Okay, it should be less than equals to r times an plus 1. But how you apply an plus 1 to an? Is less than equals to r times the absolute value of an. So you can keep continue. Okay, so how many you going backward, it will reflect in the power of k. Power of, yeah, k. Sorry, power of r. Okay, so we have retreat k times. So it pop up a factor of r to the power k. Can follow? Okay. So how is this useful here? How is this useful here? So remember, what's our job? We want to show that this infinite series is absolutely convergent. So what is the partial sum we need to look at here? What's the partial sum we need to look at? What's the partial sum we need to look at? We need to look at the absolute value of A1 plus absolute of A2 and then so on. Okay, we need to show that this partial sum converge. Okay, we need to show that this partial sum converge here. Can we use this knowledge to show that our partial sum converge or not? Can we see? Can we use this knowledge here? Okay, so where's this n come from? Where's this n come from? Actually, we are given an r, right, in between 1 and 0. And then n is also given. Okay, so this is a specific n that work with this r, so that for every term behind this n, we have this inequality here. Does it make sense? Okay. So that's why we single out this n plus k here. So meaning what? So for the first n term, we don't have control actually. Okay, we don't have control. When do we have control? Okay, we only have control after an. Okay, for example, an plus 1, okay, up to an plus k. Okay, how can we control the last few terms here? How can we control the last few terms here? How do we control the last few terms here? See the first line here. This is true for all k. So meaning k plus n plus k, n plus 1, n plus 2, n plus 3, n plus 4 all satisfy this inequality here. Okay, so for the an plus 1, I can bounded by what? R times an. Okay, an plus 2 bounded by r squared times an. And then all the way I have rk times an. So what's the last few terms here? Do you see? Do you feel familiar or not? What's the last few terms here? Yes, geometric sum. Correct or not? You can first factorize an, and then what's at the back? 1 plus r squared plus rk cube plus dot 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 plus until R K. What's this sum here? What's the formula for this sum? Huh? What's the formula for this sum? 1 minus to the K plus 1 over 1 minus R. Hey, but this R is in between 0 and 1. So meaning what? This sum actually converge. So what's the sum of infinity for this term? Sum to infinity of this term is what? What is the sum of infinity for this geometric series? High school. 1 over 1 minus R. Correct or not? Sum of infinity. Okay. So this means what? This means what? This guy, what number is this? 1 over 1 minus R is a finite number, and then all these A1 to AN is a finite number. This means what? This is just a finite number. So what we have shown is for every n, the finite sum here, finite sum of AK is less than equals to m. Okay, it's less than or equal to m. Because you need to know that this is true for all k. Okay or not? So by monotone convergence theorem, the infinite series converges. Okay, any questions so far? Is everyone following this part here? All the series, the finite term is less than m. Is everyone following here? Does everyone follow here? Because what we have shown for this inequality is true for all n. Okay, all k. Okay, so all the n plus k, all the terms behind, okay, should be less than this term here. Okay, how about before n? How about before n? Like 1 to n minus 1. Is it true that sum of a1, a2 up to an, big N minus 1 still less than m? Is it true? True or not? True, right? Because you contain all the previous finite many terms. But what have I shown you is for all the infinite partial sum after n, okay, is still less than m. Still less than m. Because I showed it for all k. Okay. What is this k doing? This k is adding, this k is increasing the n we have here. N plus 1, n plus 2, n plus 3, n plus 4, n plus 5, n plus 6. All these are less than this m here, this finite number here. Okay or not? Make sense? Okay, so we have shown that all the Sn, the n partial sum is less than m, so it converges by monotone convergence theorem because it's bounded above, and then also it is increasing because what you add is a positive term every time. It's increasing. So this n partial sum is increasing and then bounded above. So by bounded monotone convergence theorem, it converges. Okay or not? So far, any question about this? Any question? Okay, if not, tomorrow we'll continue with ratio tests using this lemma here.